So, now this will be the third lecture of this module, and because the last lecture was a little long. So, this will be the we will have only 4 lectures in this module. So, the third lecture we will have the third lecture now, and then the fourth lecture will be some practice problems. Okay. So, in this lecture I want to generalize the idea of the Fourier series and talk about orthogonal eigenfunctions. Okay. So, in the Fourier series we used sines and cosines, okay, and we expanded functions in terms of sines and cosines, but it turns out that you can expand in terms of any orthogonal eigenfunction. Okay. The Fourier series is a very useful series, okay, but there are also other series that are useful in some cases. Okay. So, I want to talk about orthogonal eigenfunctions, and then I want to talk about the general theory of orthogonal eigenfunctions, which is referred to as the Sturm-Liouville theory. Okay. So, to motivate this, let us first talk about Legendre polynomials, and these are we denoted them as Pn of x, okay, and these are polynomials, okay, and these satisfy the Legendre differential equation, which we wrote as So, this is a Legendre differential equation whose solutions are these polynomials. So, for different value of n you get these solutions. Importantly, see each value of n corresponds to a differential equation. And basically when you change your n, you get a new differential equation, okay. But the nice thing is that the solutions of all these differential equations, okay, they look very similar and they can be expressed in terms of these Legendre polynomials, okay. And I'll just write the expression. So, I mean this is derived in books, okay, we are not going to bother with this too much, but I will just say that the Legendre polynomials, okay, they have this form by 2, and you have some big expression, okay. I do not expect you to remember this expression, but you should know that it is actually possible to write such expressions. So, there are a bunch of factorials, there is 2n, so j goes from 0 to n by 2. So, n minus 2j will always be greater than or equal to 0. Okay. Similarly, n minus j and 2n minus 2j will also be greater than or equal to 0, and then you have x raised to n minus 2j. So, again in this term there are n by 2 terms, okay. So, if n is odd, okay, then you will have x raised to all the odd powers, okay, x raised to odd powers. If n is even, you will have only even powers, okay. So, you will have a polynomial that contains either odd terms or even terms, okay. Now what is interesting about this Legendre polynomials is a very interesting fact about these Legendre polynomials is the orthogonality, okay. And what this orthogonality says is that integral Pn of x Pm of x dx from minus 1 to 1 equal to 0 if m is not equal to n. Very interesting relation. So, if I take two polynomials and I take their product and I integrate it from minus 1 to 1, okay, then you get 0, okay. And if n is equal to m, this is just 2 over 2n plus 1, okay, equal to n, okay. Now there are a few things to note, okay. First is this limits, okay. So, limits are from minus 1 to 1. Second thing is that you just took a product of the polynomials and you did this, and you said it is equal to 0, okay. Now what is interesting is that we just took the product, we did not multiply by any factor, okay. Now we go back to our ideas of vector space, okay, and what we say is that this looks like a dot product. Okay. It is the generalization of a dot product. So, what we are seeing here, this whole thing is like a generalization of a dot product. Okay. And so, we use a terminology that P n of x and P m of x are orthogonal. In other words, the inner product, if I imagine these as vectors, then this, if I imagine them as vectors, this inner product is defined as -1 to 1 P n of x, P m of x dx. Okay. So, this is inner product. Okay. So, basically you can think that in this space of functions, okay, in vector space of functions. Okay. So in this space of functions, these are vectors, these are like vectors that are orthogonal. Okay. So, this is like a dot product. Now what you can do is you can write any since these are orthogonal vectors, okay, the set of vectors okay, or in you can use polynomials P0 of x, P1 of x, P2 of x constitutes a basis set for functions f of x. Okay. So, for all functions f of x, you can use this as a basis, and you can write, you can do a basis function expansion. So, you can write f of x is equal to sum over n equal to 0 to infinity a n p n of x. Okay. This is expanding f of x in p n of x. Okay. This is you can call this an orthogonal eigenfunction expansion. So, this is like an eigenfunction. Again this idea, we already saw this when we were doing the Fourier series. In the Fourier series, we took a very particular form of this P n, we took sines and cosines. Okay. But this is sort of a generalization of that. Now what is a n given by? So, a n I can use the orthogonality relation, okay, to say that if I take f as a vector and or let me write a m, then I take the inner product with P m. Okay. So, if I just take this inner product, okay, now this will be equal to, now what will happen is that I will have sum over n equal to 0 to infinity a n, and I have P n P m. Okay. But using the orthogonality, I will see that this term is equal to 0 if n is not equal to m. So, all the terms in the sum where n is not equal to 0 will be 0. So, the only term that will be non-zero is when n equal to m. Okay. And when n equal to m, P m will be 2 over 2 m plus 1. So, what I will get is a m, that will be the term where n equal to m, times 2 over 2 m plus 1. Okay. So, therefore, I can write a m as 2 m plus 1 over 2, and I can write I will just write out this f of x P m of x dx from -1 to 1. Okay. So, this is what this is how you calculate the coefficients of this expansion. Okay. So, now this is a very powerful method, okay, and we showed this for the Legendre polynomials. Okay. Now there are now the Legendre polynomials are solutions of the Legendre differential equation. Okay, they are solutions of this differential equation. Now, you could have other polynomials that satisfy other differential equations, and they could also be orthogonal. Okay. For example, you could have, let us say, the Hermite polynomials. Okay, so incidentally, the Legendre polynomials appear in the rotational states, rotational degrees of freedom of a particle. The Hermite polynomial appear of a molecule. Hermite polynomial is used to describe the vibrational degrees of freedom of a molecule. Okay. So, that is a harmonic oscillator. So, they appear in the solutions of the quantum harmonic oscillator, whereas Legendre polynomials appear in the solution of the quantum rigid rotor. So, the Hermite polynomials, now these satisfy the differential equation y double prime minus 2 x y prime plus 2 n y equal to 0. So, they satisfy this differential equation, and these are written as h n of x, okay, is a solution of this differential equation. You have h 0 of x equal to 1, h 1 of x equal to 2 x, h 2 of x equal to 4 x square minus 2, h 3 of x equal to 8 x cube minus 12 x, and so on. Okay. So, what is important is that the even terms, even polynomials, they contain even terms, and odd polynomials contain odd terms, that is odd powers of x. So, therefore, you can say that h n of minus x is equal to minus 1 raised to n h n of x. So, these Hermite polynomials are odd. If n is odd, then h n of minus x is minus h n of x. So, they are odd functions. If they are even, if n is even, then it is an even function. Okay. So, now these Hermite polynomials, they satisfy an orthogonality. So, their orthogonality is slightly different. This is slightly different. This satisfies, this is written as integral minus infinity to plus infinity h n of x, h m of x e to the minus x square dx equal to 0 if n is not equal to m, and equal to root pi into 2 raised to n factorial if n equal to m. Okay. So, now in this case you notice that the limits go from minus infinity to infinity, and there is this function here. This is referred to as a weight function. So, we say that Hermite polynomials are orthogonal with respect to this weight function. So, Hermite polynomials are orthogonal with respect to weight function e to the minus x square. Okay. So, these are the two, this is another kind of orthogonality that is there. Okay. Now, we can generalize this. So, the general description of orthogonal functions is called as Sturm-Liouville theory. Okay. So, this is the theory that will help you understand what should be the limits, what should be the weight function, and so on. Okay. So, here what is done is you write a second order ODE in the following form. You write it as p y prime the whole prime plus q plus lambda r y equal to 0. Okay. So, p is a function of x, okay, and q is a function of x, r is a function of x, lambda is a scalar, lambda is a real, lambda is a scalar, are continuous in some interval, you take some interval a b. Okay. So, a b is some interval in x. Okay. So, and what else, some other conditions we will demand that p of x is greater than or equal to 0 in a b, and r of x is greater than or equal to 0 in a b. Okay. So, this is a differential equation. So, you take this differential equation, I will call it equation 1. Now, I wrote it this way, I mean basically this is a general second order linear differential equation. Okay. Second order linear homogeneous differential equation can be written in this form. Okay. And now the, so suppose you have this differential equation and you have the boundary conditions. So, the boundary conditions at A, so A and B are this, A and B are the is a range of x, is the allowed values of x. So, the boundary condition I will write as alpha 1 y of A plus alpha 2 y prime of A equal to 0. So, this is the boundary condition at A, and you have beta 1 y of B plus beta 2 y prime of B equal to 0. So, these two are the boundary conditions, boundary condition at A and B. So, A and B are the boundaries, okay. And we want at least one of alpha beta not equal to 0. So, one of these four, alpha 1, alpha 2, beta 1, beta 2, one of those should not be equal to 0, and we will assume that alphas and betas are real, alpha beta are real numbers. Okay. So, here, so lambda is referred to as an eigenvalue, okay, and lambda should be a scalar, it can be a real or a complex number. Okay. Now, this is called a Sturm-Liouville problem. So, suppose you have this differential equation with this boundary conditions, this constitutes what is called a Sturm-Liouville problem. We will refer to it as SLP. Okay, the Sturm-Liouville problem. So, this is what constitutes a problem, a Sturm-Liouville problem, and you find that you can write a whole lot of differential equations in this form. Okay, so this is not a very restrictive form. You can easily see that you can write your Legendre differential equation, your Bessel equation, your etc. in this form. Okay. Now, suppose if so there are various special cases. Okay. If P of A not equal to 0 and P of B not equal to 0. Okay. So, we said that P of x has to be greater than or equal to 0. So, it cannot be negative, but it can be 0. But in case P of A and P of B are not equal to 0, then this is called a regular Sturm-Liouville problem. If P of A equal to 0, okay, then boundary condition at A is not needed. Okay, so we don't need this boundary condition. We don't need the top boundary condition at A. Okay, if P of B equal to 0, then boundary condition at B is not required, not needed. Okay, so if and these two are referred to as singular Sturm-Liouville problems. Okay. And the third case, if P of A is equal to P of B, okay, then we can demand y of A equal to y of B and y prime of A equal to y prime of B. Okay. And with this we constitute something called a periodic Sturm-Liouville problem. So we can look for solutions that satisfy this. So, there exist these solutions and this constitutes a periodic Sturm-Liouville problem. Okay. These are the various types of Sturm-Liouville problems, and for each of these the Sturm-Liouville theory says that there exists. So according to Sturm-Liouville theorem, first is that there exist solutions y n of x for eigenvalues lambda n. Okay. So, that means you have you have eigenvalues like lambda 1, lambda 2, lambda 3, and you have solutions of y 1 of x, y 2 of x, y 3 of x, etc. Okay. So, there exist these solutions. Second thing is lambda 1, lambda 2, etc. are real, and the third is that corresponding to these lambdas, okay, so y's are orthogonal. So, solutions are orthogonal with respect to weight r of x, that is integral y n of x, y m of x from a to b, this is the limit r of x dx equal to 0 if n is not equal to m. Okay. So, this is a very powerful theorem, and notice that just by looking at the differential equation. So, just by looking at the differential equation and the boundary conditions, we can immediately imply that the solutions, okay, the solutions now notice, if you change the value of lambda, you will get a different differential equation. Okay. So, and this is exactly what happened in the Legendre polynomials or the Hermite polynomials. For example, in the Legendre polynomials, your lambda will look like n plus 1. So, you have, this is what your lambda looks like. Okay. So, just by having a differential equation in this form, okay, and having suitable boundary conditions, you can get orthogonal eigenfunctions. Okay. So, obviously we said that if P A equal to 0, then boundary condition at A is not needed. If P B equal to 0, boundary condition is at B is not needed, and if both are 0, then then you do not need any boundary conditions, and you can just write this orthogonality. Okay. Now once you have this orthogonality, then you can expand your functions in terms of these orthogonal functions. Okay. So, I will conclude this lecture here, and what I want to emphasize in this is that there is a very general theory of orthogonal function expansion, okay, and this is called the Sturm-Liouville theory. And this theorem is extremely powerful because you can just look at differential equations and you can identify that the solutions should be orthogonal eigenfunctions. And once you have orthogonal eigenfunctions, you can take any function and expand in those. The place in chemistry where you see this really in action is quantum mechanics. in fact the whole of quantum mechanics, the very postulate of quantum mechanics is related to a kind of operator called a Hermitian operator. This operator has real eigenfunctions and it has eigenvalues, it has real eigenvalues and it has orthogonal eigenfunctions. And in fact the important thing about quantum mechanics is that you can almost write the most common equation that you see is the Schrodinger equation or the eigenvalue equation for the energy for the Hamiltonian operator, which is actually a second order differential equation, and you can show that its eigenfunctions should be orthogonal, okay, and its eigenvalues should be real. So, the energy is the eigenvalue which has to be real. So, in fact the whole of quantum mechanics is founded on this Sturm-Liouville theorem, okay. It is an extension of SturmLiouville theorem to complex functions, okay. And so I will conclude here. Now in the practice problems I will try to show you how to write various classic problems as Sturm-Liouville problems and how to use the orthogonality to do various simple integrals in quantum mechanics. Thank you.